answer all the questions you see up there. Okay? Zach, go for it.
I don't see any questions.
What is electron?
Okay, and really I'm referring to what is electricity.
The flow of electrons in a complete circuit.
Magnetism is?
The act of repulsion and attraction with like or unlike poles.
That's the idea. Okay, and how are they related?
Because electricity can generate magnetism.
Good.
As Oersted shows that.
That's what Hans Oersted said, and exactly. That's the first concept that we built on so that we could make our electromagnets. Now we're going to build on another discovery made by that dude, Michael Faraday, that shows that the opposite is true. That'll be our main focus today. What's V?
V stands for volts.
And voltage is like the
pressure.
And I is?
I is, doesn't stand for amps.
Okay, which is
and
the?
Amps is like the rate of flow.
Also called the what? The rate of flow is the what of the electricity? We measure with a little ammeter. Amps is a measurement of
Like how much?
What do we call that? It's like water has it, a stream has it, a river has it.
Oh, current.
Current. Okay?
And then R is resistance, and that's measured in ohms with the omega symbol.
And what does that do to the flow?
That increases it, like.
Increases it?
No, decreases.
Decreases it. Okay? A battery is?
It's makes electricity through a chemical reaction with two electrodes and one electrolyte.
Got it. And a coil. Tell me 3 things about a coil that you would need to consider to make sure it's as strong as possible.
Make it out of a permanent magnet.
Okay, well, use iron, nickel, or cobalt, is what you're saying, right?
Yeah.
Okay, what else?
You have to make narrow turns.
Get as many turns as possible, okay? And?
Use a small core.
Small core, so you can get more turns. All right, anything else? That's good.
Yay.
You got another one?
The type of wire.
Yeah, if you use that magnet wire, the enamel wire, it lets you get closer with each turn, also lets you get it closer to the core. And the reason I asked that question today is because what we're going to explore today has to do with a generator. Those same factors that affect an electromagnet will affect a generator. Okay? So we're going to be putting all the pieces of your knowledge together to answer a very basic question today. And we're going to be doing an assignment called electromagnetism. Most of you will finish that in class. If you don't, you'll be able to finish it at home. We'll grade that tomorrow. And that's kind of like your notes today. That's why all you have is a pencil. I'll go through each question. We'll talk about it. I'll show stuff up here. And you should all have the right answer because I will read it out to you several times. If you can't keep up, it's more important that you get the concept. Because if you got the concept, you can finish writing, filling in the blanks at home. But it starts with answering our first most basic question, which I think I threw out at you on the very first day here. Let's imagine we crashed into that island. We're trying to power the radio. We talked about several ways that we can produce electricity. Some of them really wouldn't work for powering the radio on the island. Which ones that we talked about would not work? Nathan?
Static electricity.
Why would static not work?
It's a burst and it's not a flow.
Exactly. It's not going to get the job done because in order to have that radio powered, it needs to stay on long enough that I can say, help, help, we crashed on the island, our coordinates are, and give all the information. If all I get is a quick little burst, like you get when you stuff your feet and touch, that's not going to be enough. It's not going to give enough flow to keep that radio on. So whether we got that from scuffing our feet on the carpet, which I don't know where you did that on the island, or you got it from lightning, it's not going to provide the flow that you need. Some people have suggested, well, let's put a lightning rod on the top of the mountain, and then we'll attach the lightning rod to one wire on the radio, and the other wire will go into the ground. Put that away, Matt. You don't need that. Okay. You're absolutely right. It would blow up the radio. It would burn out all the circuitry. Why? It's too much power at one time. Okay, it's like me turning on a fire hose. I can knock you across the room. I turn it off immediately, and you might not get drowned by it, but it'll knock you across the room and do damage to you. Okay, we're not going to have that flow necessary to fill up a pool. That's what we need. We need to have not just a short burst, but a continual flow. So static electricity, by its name, static means not moving. And we build up a charge, it doesn't move, and then we discharge, and it moves all of a sudden and it's over with. So that won't work. What else would not work?
Failing to walk together
Why not?
because you can't really produce electricity. Well, you do, but not enough power.
Well, you create short little bursts again. Again, the flow is not going to be nearly as much as you have with lightning. The current is very low. Like the Van de Graaff generator, our static thing, is very low. We couldn't keep the flow going. So if you had to power that radio, man, you'd have to bang on the rock super fast because all you get is just burst, burst, burst. And even still, you wouldn't be able to keep that flow long enough to power the radio. I talked about another one. Remember the thermocouple? Two pieces of metal that have been held together and we heat up that connection. Well, that's not going to work because, again, it only provides a little trickle of flow. We need more flow. We need to keep it going. We need what we get electricity from out of the wall. We need a generator. Anyone think they could make a generator with raw materials? Think you can do it? What would you like to have to build your generator?
A wire, copper wire.
Okay? Wire. I will give you a wire. Come on up here so we can see because we want this on the podcast. Here's your wire. What else would you like?
I need like,
What are you doing there? Why are you doing that? Ah, okay. Well, turn this way so we can all see. You're making a circuit. See, in order to do what we're doing today, in order to answer this question, how to make a generator, how to power the radio with a regular flow of electricity, controlled flow, we need to know the answers to all those questions. And you know, in order to have electricity, we need to have what? What is electricity? What is electricity? The flow of electrons through a circuit. Where do electrons come from? Atoms. Does this copper wire have electrons? Yes. So he's got himself a circuit, a complete path. He did that. And now we need to get the electrons to flow. So go ahead, get them flowing. Flow away.
You need like some sort of magnet.
Some sort of magnet. Why a magnet?
Well, because, I don't know,
Just because. All right.
and you need motion, but I don't know, you need to like, I wouldn't know how to build that of it.
What's up?
It's like a turbine.
Okay, just give me your best shot. Because actually, you have all you need right there. He actually knows his stuff. He's right on it so far. You have all you need right in your hands to make electricity. So go ahead. Get some flow. No? You're so close. Go back to where you were. You had your circuit there. Okay, now let's think this through, guys. You can figure this out. So we know we need a circuit. Hold the circuit there. Where are the electrons that you're going to get flowing? Where are they? Where are they located? Yeah, but the ones you're going to get flowing through your circuit, where are they right now? In the wire itself, right? The electrons in the copper, they move easily. That's what makes this a good what? Conductor. Because we can move those electrons easily. And we know from our discussion of magnetism that the smallest magnet is really a what? Smaller than that. An electron. Whenever an electron's moving, it's like a little magnet. Now, some things can be magnetized, some things cannot. Can you magnetize copper, make it a permanent magnet? No, because it has what kind of electrons? Paired electrons. It's got one spinning the other way that cancels it out. So we can't make this a permanent magnet, but that doesn't mean that we can't influence those electrons. So what we need to happen here, we need the electrons in this wire to flow, to move, to go around. And we know that each electron is like a tiny little magnet. Okay? Can you picture it? So we need to be able to reach in there, get a hold of those tiny magnets, and make them move. Can you do that? All of this work. Ah! Believe it or not, he just made electricity. Everyone, give him a golf clap. Golf clap. That's good. You got it. You can have a seat. Thank you. Okay. So the secret to making a generator, to generating electricity, you only need 3 things. A wire that you create a circuit in, a permanent magnet, and motion. Those are the ingredients. Okay? It's kind of the opposite of what Oersted said. Oersted said that, hey, if we've got electricity, and the electricity is flowing through a wire, we get magnetism. Well, old Michael Faraday here starts scratching his head and going, that's quite interesting. Electricity makes magnetism if it's flowing. I wonder if magnetism and a wire with motion will give you electricity. And he did a simple experiment, looked something like this. Guess what he got? Electricity. You can make electricity. If you provide this form of energy, motion, and you use magnetism, you can move the little electrons. And this is the main concept. Before I pass this out, I want to make sure you guys got this main concept. Is that in this wire are little miniature magnets. Okay? And we know that north and south will attract. So I bring one end of this magnet to it, I can motivate those little tiny electrons to follow this magnet. And I can get them to move through the wire. Now there is something important about how we move, okay, and about the magnet itself. And those are the details we're going to look at. But put simply, by attracting those little miniature magnets, the electrons, to this permanent magnet, I can get them to move. And as long as I'm moving, the electrons move. Imagine this. Imagine I have a whole bunch of magnets just stacked up like this. I can knock them over by not even touching, by using this to attract this one and drive it into the next. That's precisely what's happening. You following that? How many got that? Raise your hand. Don't worry about it. Okay. I'm going to give you 2 papers here. The first one is the assignment that you can write on. It has a place for your name. Go ahead and fill that in when you get it. The second one is just something we'll use to refer to some pictures. What I was hoping you would get from this whole thing is that electricity is not just something that engineers and very smart people can understand. It's really pretty simple. A wire, a magnet, in motion, and you've got electricity. It doesn't require all this high-tech stuff. So again, get your name, date, and period on this when you get it. The second one, do not write on. Maybe a short one, so we might have to go with that. Actually, here. Let me know if you have any extras. All right, I am going to give you the answers to each of these, so you don't need to worry about that. Are there any extras of those things? No? Don't worry about the definition, because I will read it out to you, or the answer to each question. I'll read it out to you when we get to it. The first one refers to that picture on page 206, which is on the very top, and that's whose experiment. Who did that one? Doesn't say on the paper. You should have already learned it. Hans Oersted. Very good. The teacher who did the demonstration. We've talked about this before, but once again, he had a compass in his classroom. He had a battery. That was really the only practical way of making electricity at the time. we didn't have this generator thing that we'll be talking about in a little bit. And he saw that when you hook it up, the needle would move. It affected it. It proved that electricity flowing through a wire makes magnetism. It grabs a hold of that compass needle and hangs on as long as there's current flowing. Okay? So that's the answer to your first question already. What kind of energy does electricity produce in this experiment? And the answer is magnetism. If it's a short line, very short line like that, you only need the few words or word. If it's a longer line, you'll need to write in a complete sentence. Make sure you do that. How can a magnet produce electricity? Now you need to flip the page to 221. And you see something similar to this. We'll be using this a lot today to evaluate this whole thing of a generator. In order to understand this, you have to understand magnetism. And we looked at that already. I showed you a bar magnet, you drew one in your homework, and I showed you a horseshoe magnet. I said, make sure you remember what this looks like. In case you didn't, I'm going to show you again. When we sprinkle the iron filings around that magnet, we see that they line themselves up with this field of attraction that surrounds the magnet. That field is called the blank blank of blank. Not one of you remembers. That's embarrassing. The field of attraction that surrounds the magnet. You took this in your notes. I'll get you started. Magnetic blank of blank. Something force, yeah? Getting there. Yes? No, Scotch. Magnetic. You guys need to go back and review your notes.
Oh,
We
okay.
took this in our notes. You should know this, yes.
Magnetic lines of force.
Magnetic lines of force. I've shown this to you. This is the third time now. You should have this. Magnetic lines of force. The lines aren't something you can see. They surround a magnet. You can feel the effects. But when you sprinkle iron filings on, now you can see exactly the direction that they run. And I told you before that those lines of force were going to be real important. And it's useful to be able to look at a magnet and go, I know what those lines of force look like. Because I drew them on my homework. I know we got little curved lines that connect the two poles. And we got ones that go out like this, way out. Remember? Does this ring a bell? Those lines, whether we have filings on them or not, are called magnetic lines of force. You had it in your notes, one of the terms. And we know from that homework that the pole, the attraction is greatest at the poles, the north and south pole, and gets weaker as you get to the center or farther away. Weaker out here. These aren't lining up very well. These are. The closer we get, the stronger that attraction is. Down here, pretty weak. They're not really lining up to those lines of force. If we go up this way, you can see there's more and more lines of force. And I can even feel how strong they are because I can feel the resistance as I try to move those filings. They don't want to move. They want to hang on because the lines of force go across like this. So every time I show you a horseshoe magnet, you should see that in your mind's eye. You should be able to picture those lines of force, just like you did with the bar magnet. How can a magnet produce electricity? Well, Nathan did it, I did it. First we need what? What are the ingredients? A wire. Then we need a magnet. And the secret ingredient? Motion. Okay, let me just prove to you, because I know some of you probably didn't believe me, that I was making electricity. So I'm going to hook this up here. I got my wire. I got my magnet. And I got a little meter here that's supposed to tell me when I have flow, when I have current. That should be a little m, by the way, milliamps. Alright, so be prepared to be dazzled. I'm going to make electricity with just a wire and a magnet. Here we go. You see it?
No.
You see it move? Yeah, a little teeny tiny bit. It's just barely moving. Okay? Now look at how I'm moving the magnet. What I'm trying to do is I'm trying to go through those lines of force. If I were using this magnet, remember where those lines of force are? When they go sideways, I'm going to go through those lines of force. You see the needle move? Okay? Not too impressive, not a lot of current. But I can improve on that. And you see it there in your example. How can I improve on that? Nathan?
Coil the wire.
Coil the wire. So I'm going to remove this simple single wire and I'm going to replace it with a coil. This coil happens to have 5 loops or 5 turns. Now I'm going to move the magnet through the wire through the magnet, and it's going to go through. It's going to break all those lines of force. Remember, there they are. And as that wire goes through, it's going to break all those lines of force. And you'll see I get noticeably more current, more flow. Okay? And the reason I'm getting more flow, well, who can tell me? Why am I getting more flow from the white one than the red one? Brianna? Making it a circle doesn't create an easier path for it. Yeah.
It's like more compact, so all the electricity stays where it goes.
Okay. Well, let's think on the most basic level what I am doing. When I'm doing this, I'm breaking lines of force, and those are causing the electrons right here, the part that went through the magnet, they're causing them to move. Okay?
It's like the same as doing it 5 ago.
Exactly. It's like the same thing, except instead of just affecting one little piece of wire, I'm doing it to 5. I'm influencing more of the wire. You know, when I show this to classes, they often say, well, I know how you can improve. Get more magnets. Cover the whole thing in magnets. Well, I got enough magnetism right there. I just need to get it onto more of the wire. I need to affect more electrons. You see how that's going to affect more electrons? More parts of the wire are going to be going through. This is going to produce 5 times as much as this. Because I have 1, 2, 3, 4, 5 turns, all doing the same thing. This only does one. One wire breaks it. Here, it's like having 5 wires breaking those lines of force. The answer is to number 2. How can a magnet produce electricity? We use a conductor to break the lines of force. You use a conductor to break, magnetic lines of force. Third time, we use a conductor to break the magnetic lines of force. We use a conductor to break the magnetic lines of force. Matt, you had a question?
Yeah, so when you do that, active power of the radio.
No, it's still not enough. I need to improve on that. That's only 5 turns. This is a tiny amount of current that I'm making here. 2 milliamps isn't going to be enough to power your solar calculator. Okay? I need a lot more. That means I'm going to have to improve. And I'm going to ask you that in a little bit, how we can improve on this design. But right off the bat, you probably noticed that when I do it up here, I get a lot more. Why am I getting more from this? More turns, exactly. A bigger coil, more turns. Now the next question, 2B. If we're going one direction, we're moving that magnet through the coil in one direction, we notice the current flows one way. I pull it out, it flows the other way. And that should make sense to you, because in essence, the electrons are following the magnet. Remember my magnets all stacked up like dominoes, how they would follow? I could get them to go to the right or go to the left. Well, that's what they're doing. They're following the magnet here, in and out. So that should explain the answer to 2B. How is the direction of the current affected by the magnet's motion? As the magnet reverses, so does the current. As the magnet reverses, so does the current. The magnet reverses, so does the current. I was just getting too hot, right? 2C. How does the speed of the movement affect the current generated? I think you could guess. What do you think? Faster you move, the more current you're going to get. Faster you move, the higher the current. The faster the movement, the higher the current. The faster the movement, the higher the current. Now, a lot of people get confused by this. When I put a meter up and you see a meter like this, where, like the one you worked with, your ammeter, a galvanometer you worked with when you made your wet cell, it had 0, but it could go negative or it could go positive. And a lot of people mistakenly think that negative, bad, positive, good. No. If we're trying to get flow, we don't care which direction. We don't care if it goes to the right or to the left. I don't care if the stream runs this way or runs that way. If the water's moving, we're doing work. If it's sitting at 0, we're not doing work. Got it? Okay? And when I take the magnet and I go in and out, the faster I do that motion, the more time it spends away from 0. If I slow down, notice what happens. It falls back to 0. Okay? So if I go really slow, it spends more time at 0 than if I go faster. It spends less time at 0. Does that make sense? So that's why we get more current when we go faster. We're doing more work, we ought to get more current. We're breaking more lines of force. The magnet has those wires going through, breaking them more often than we are when we go slower. 2D says, what types of energy changes occur in this particular example? Well, we can figure this out and we'll trace it backwards. First of all, right now I've got nothing. Why? No movement. The electricity comes when I have magnetism and a wire and motion. Okay? When I've got motion, I get electricity. Where did I get the energy for my motion? That's mechanical energy. I'm moving a machine. Where did I get the energy to do that? What was the next thing? In order for me to move a muscle, I must send it a signal. What kind of signal is it? Electricity. Okay? How did my brain and my body make electricity? It works like a giant battery, which makes electricity through a chemical reaction. How did I get the energy? How did I get those chemicals? I'm going to spit it out, please. How did I get those chemicals? Food and water. Okay? How did the food I ate get the energy to grow? The sun. And if you don't know how the sun got its energy, it's through an atomic reaction. It's atoms of hydrogen fusing together to make helium, releasing light and heat. So basically, this you're seeing here can be traced all the way back to the sun. Sun makes light and heat. Light and heat reach the earth. You don't need to write it down yet. Light and heat reach the earth, helps the plants grow. Animals eat the plants. I eat the animal or the plant. Gives me chemical energy to make electrical energy, to move my muscles, to create electrical energy from a magnet and a wire. It's all quite simple, huh? The answer is, light gives the plant chemical energy, which gives me mechanical energy to move the magnet, producing electricity. Light gives the plant chemical energy, which gives me mechanical energy to move the magnet, producing electricity. Light gives the plant chemical energy, which I use in mechanical energy to move the magnet, producing electricity. 2E. How can a stationary magnet produce electricity? Can a stationary magnet produce electricity? Yeah. There's two ways to get hit. One is you can sit there and I can bring my fist to your face, or I can hold my fist there and you can run your face into it. Okay? Either way, you get hit. I can hold the magnet and move the coil back and forth, or I can keep the coil stationary and move the magnet back and forth. As long as the lines of force are being broken, we still have current. Current would still be generated by moving the wire. That's 2E. Current would still be generated by moving the wire. I hope you're writing these in complete sentences. Put your first one. Current would still be generated by moving the wire. F. Okay, I'm getting current there now. Would current still be generated if the wire were broken?
No.
Ooh, big shot. No, because I don't have a complete circuit. So the answer is no in the first space. In the second space, there is not a complete circuit. Period. No, in the first space. In the second, there is not a complete circuit. Okay, we're still referring now to the picture on page 222. So if you haven't switched over to that one, go to page 222. That's very similar to this. So whether it's a coil standing there and moving a magnet back and forth, or it's going sideways and we're using a bar magnet, either way we're doing pretty much the same thing. We're breaking the lines of force. And question number 3 says, when a magnet moves towards a coil of wire, blank is detected in the wire. What is this detecting? What is this measure? What about the electricity? What is MA? Milliamps. And milliamps is a measure of current. Yeah. Current is detected in the wire. That's what you're detecting. It's the flow. Got a little meter hooked up to your water supply to your house. And as the water rushes through the pipe, it keeps track of the number of gallons going through there every minute. Well, this is the equivalent for electricity. It keeps track of the flow. And as I change direction with the magnet, what happens to the direction of the flow? It changes, it reverses. Second space then is reverses. First one is current. The magnet moves towards the coil of wire, current is detected in the wire, it reverses its direction when the magnet moves away. And again, it doesn't matter if it goes to the right or the left. It's if that needle is moving and away from zero, then we have current. Water flowing that way or that way is still going to do work. Number 4. Now you can show me that you really understand this. You can tell me 4 ways. It says 3, but you're going to give me 4 ways of generating a larger current. And it's just like we had with our coil that we built for magnetism, and now it's going to work in reverse. So give me 1 way to make more current.
A bigger magnet or a bigger coil.
A bigger magnet or a bigger, when you say bigger coil, what do you mean? Bigger round?
More round.
More turns, yeah. You can see that with this one, we don't get nearly as much as we do with this one. Big shot. We've got more wires breaking through the lines of force. So we're going to create more current. Don't need to write it down yet. I'll give you the whole thing here in a second. So more turns. And what was the other thing you said?
More moving the magnet faster.
Yes, it will. We already kind of talked about that. The faster you move this, the more time it spends away from zero, the greater the current. What else? Move it faster, more turns.
More powerful magnet.
Yeah, stronger magnet. Got more magnetism, it's really going to get the electrons moving more. And 1 more.
A different wire.
Yeah, it's somewhat related to the wire. A stronger magnet, if that makes sense to you. You're going to have those lines of force are going to be reaching out more. But even if I can't make this magnet stronger, and I can't add more turns to this, I still can improve on this design. What could I do? Huh? Move the coil. Well, yeah, move both at the same time. Well, yeah, I could do that.
Make them around the same size, so they're
There you go.
put together.
get it close, okay? The closer that wire is to the magnet, we know the magnetism is strongest right next to it, ideally touching it, right? We get a little bit away and it gets weaker. Out here, much weaker. Out here, it's almost gone. You won't even detect it. So the closer that wire is to the permanent magnet, the more current you're going to generate. You can get that smaller. In a real generator, they get that coil so close to the magnet that it's almost touching. We don't want it to rub up against it because that would wear through the covering. But we want it to be super close because closer is going to be stronger, more magnetism. So the 4 ways, not 3, the 4 ways are, we can increase the current by moving the magnet and coil closer. We can increase the current by moving the magnet and coil closer. You're going to need to write small for this. We can increase the current by moving the magnet and coil closer. Adding turns. Moving faster, or using a stronger magnet. Adding turns, moving faster, or using a stronger magnet. Yep. We can produce a stronger current by moving the magnet and coil closer, adding turns, moving faster, or using a stronger magnet. It should all be in sentences. Make sure you put your periods on. Number 5. Still referring to that same picture, which is just like this. If the magnet were moved in and out 15 times in a minute, how many times would the current change direction? Before you answer, watch. In and out. Okay? In and out. That's all you're looking at. In and out. How many times does it change directions? If we do that 15 times, how many times will it change directions? 30. Anybody else? 15. Okay? People confuse the number of directions we're going with the number of changes in direction. 15 is the answer. Look at it this way, guys. I'll be the needle, okay? Here's the magnet going in and out. I'm following the magnet. Okay, I was going this way, and now the magnet goes out, I go the other direction. How many directions did I go? 2. How many times did I change directions? Once. I was going this way, now I'm going the other way. That's one change in direction. Get it?
Then you change that.
Well, then that's the next one. So that counts for number 2. You see? Left, right, left, right, left, right, or right, left. You guys, right, left, okay? It's going in 2 directions every time I do that, but it changes from going right to going left. That's one change. So 15 times in and out, that's 15 changes. Number 6, if the coil was moved instead of the magnet, what would happen? What do you think?
Same thing.
We would still generate a current. And that's what you need to write. Full sentence there. I know it's a short line, but you can do it. A current would still be generated. The current would still be generated. Second part of that. Why? Why is the current still generated, Matt? Why is the current still generated when I do this? Because we're still doing what? I need more specifics. Give me a term. It's the main concept of this whole thing. We looked at the beginning when we looked at this, Matt. What are those things called? Okay, and what are we still doing? Breaking. There you go. We are still breaking the magnetic lines of force. Number 6, second part. We are still breaking the magnetic lines of force. Okay, now, flip to page 223. These are all related experiments, except for the very first one I showed you was Oersted's. All the rest of these are Faraday's. Faraday's the one that discovered that not only can electricity make magnetism, but the opposite is true. Magnetism can make electricity. And that experiment you see there is just like I showed up here, except with a meter, doing this, okay? How does this compare with this? What do these both have in common? This is a bar magnet, this is a horseshoe magnet, this is a coil, this is a single loop. But what do they have in common? Okay, and how would you describe the current created by that type of motion? What happens to the current? Look at the meter. What happens to the current when I do this? What happens to the current when I do this? What does it say on the meter, guys? Does it always go in one direction? No. The meter shows it's switching. It goes one direction, then the other direction. In fact, both of these do exactly the same thing. This one just doesn't work as well. This doesn't produce as much current as this one. You see, in this one that you're looking at right now with a horseshoe, when I go down through the lines of force, the current flows one way. When I go up, it flows the other way. In order to go from moving down to moving up, what do I have to do in between? Stop. Laws of physics say if I'm going one direction and then I want to go the other direction, I have to stop in between. Okay? I can't suddenly be going this way and then going that way. By the way, that's one of the ways you identify a UFO. Did you know that? This is a test to see if what you saw is a UFO. Okay? Because normally our spacecraft, our airplanes, they fly, they want to change directions, they have to do it gradually. They can't be going like this and then suddenly take off in a totally new direction. So if you see an object in the sky that's moving along like this and then it suddenly changes direction, darts off, one of the things that they'll ask you. Rapid change in acceleration, or it's hovering there and suddenly, boom, it takes off like a dart. Okay? According to our laws of physics, if we're going to go one direction, in order to go the other way, we have to slow down, stop, and then reverse. And what happens when I stop? It goes to zero. Same thing's true on this. So both of these will produce a current that changes directions. That's the answer to number 7. Both produce a current that changes directions. Both produce a current that changes directions. In essence, the electrons are following the magnet. Flip over to the back. We've got 3 more. This is all just pretty much rehashes the same thing. If you understand it, you should be able to answer these on your own. Also looking at that same picture. What happens when the wire is momentarily motionless as you're changing direction? What happens there? Yes? No. What happens when the wire is momentarily motionless as it changes directions? The current stops. You can see it on the meter there. As I change directions, it goes the other, drops to zero. It's only when I'm actually moving that I have current. As soon as I stop, it goes to zero. No current is generated. It's the answer to number 8. No current is generated. Number 9, Zach?
What? No, I was gonna ask you something.
Yeah.
If you go like really slow with the magnet, like really slow, does it still generate a current?
Proportionate to the speed, it's going to spend a lot more time at or near zero. The faster you move, the more time it spends away from zero. Think of it this way, if this is gallons per minute, and you're filling up your tank and it's at 1, and mine's at 2, I'm going to fill up my tank sooner. I've got more gallons per minute coming out. So the more time I spend away from zero, the faster I'm cranking out electrons, the more electrons are going by every second. So if you go really slow, it'll have time to drop back to 0 every single pull, okay? Or it'll spend more time close to 0. There is a point where you're going so slow you're not going to generate hardly any current at all. Number 9 says, what happens when the wire moves parallel to the magnetic lines of force? So now instead of doing this, I'm going to do this. Because remember, those lines of force go across like so. What happens?
Nothing happens when you're not moving the electron.
Yeah, if you're not breaking the lines of force, that was the key. This is not going through them. This is going with them. You know, if I had my fingers here, it would be going right in between. It's going with them. It has to go down. It has to break through those lines of force. It's hard to simulate on this guy because it's hard to go straight up and down. But if I go up and down, you'll see little to no current. I'm still going a little bit to the sides. It's hard to go perfectly up and down. But you can't make current. You've got to be going back and forth, in and out. No current is generated, the answer to number 9. And finally, number 10. If you haven't gotten the concept now, you haven't been paying attention. What role do magnetic lines of force play in the generation of electricity? What has to happen? They have to be broken. They must be broken to generate electricity, is the answer. They must be broken to generate electricity. Didn't get any of these, you can go back and watch it on the podcast later. They must be broken to generate electricity. Okay? Now, just to show me for sure that you got this concept down, that you truly understand this, let me just show you a few things here, and you tell me, you make a prediction. I'm going to take this magnet, I'm going to use the north in, and I'm going to go in through this middle coil. And you saw it went to the right, and when I pull it out, it goes to the left. Got it? I'm going to use that same one, I'm going to do the bottom coil. In, out, went right, left. Why did I get more on the bottom one? More turns. Okay, now, little deductive reasoning. I'm going to flip it over. I'm going to use the south pole, and I'm going to go in. Which way will it go first? Everybody, right or left? Left. So not only is the direction I'm moving important, but so is the pull. Get it? I pull it out, it goes to the right. Same thing on the bottom. Left, right. Okay? Now, I want you to tell me what I would do with these two magnets if I wanted to generate more current by using 2 coils. What would I do? I want to use 2 coils, 2 magnets. What would I do? Explain.
Like,
North or south going in or out on this one? North going in, okay? So I want it to go more to the right. And what do I do on the bottom one? Okay, so let's watch again. North goes in on that one. And now I'm going to have south go in on this one. See that? Did that help it? Well, let's see. What do you think will happen when I use that together? North on one, south on the other, both going in. Will it go to the right or the left? I heard stay in the middle. How many say it will go to the right? How many say it will go to the left? How many say the south's on the bottom, the north's on the top? How many say it will go to the left again? Okay, how many say it will go nowhere? A few of you? A few of you voted twice. Okay, here we go. Which way did it go? Okay, why did it go left?
Because like the north and the south,
They do the opposite.
yeah, so the north, since it has less coils, it's like taking away how many coils the south has. So to be just like putting the south, it's like half of that coil.
Because this one's stronger, the effect of the south one was greater than the effect of the north one. Okay? So the north one didn't go as far to the right as the south one went to the left. It's like minus 10 plus a positive 5 is -5, and we were still on the negative, we were going this direction. Okay? If I want to use the two together and actually make it go more to the right, what would I do?
Put both on the north.
Put both on the north. So north on this and north on the bottom, use them together. Now the line. This happens. It's a very sensitive meter and it responds to static charges. But anyway, I use them both at the same time, and you can see it definitely moves farther, faster with both. Okay? So the key point of this that I wanted you to get is not only is the direction important, okay? The electrons will follow the direction of the magnet, but so is the pole, whether we're pushing or pulling. So if you want to improve on this design, the problem with this design, not enough turns. Plus, you waste a lot of energy going in and out, in and out. Better, more turns, okay? But you still have to keep changing directions. You have to stop, switch directions, and go the other way. The best way, the way to really improve, is to use motion that goes in a circle, so that this can be hooked up to a crank, a handle, and you could crank that handle, or it can be hooked up to a big water wheel, and you could have water turn that wheel for you. And am I breaking lines of force if I do it like that?
Yes.
Yes. And that's really how they design a typical generator. We'll look at that more later. I need you to pass up the handout. You can put away the other one. We'll be grading that tomorrow. And if you guys want, we can have a little fun with